Good morning again to everybody. We have come to our last week in this course, and as I mentioned in the previous lessons, in place of the usual lessons on transient phenomena, this year I decided to include some, give us the chance of employing many of the analytical techniques introduced at the beginning of the course when we introduced complex analysis. What we will start doing today is the analysis of another classical electromagnetic configuration, and again the name of Sommerfeld comes to the fore. In the last week we considered the Sommerfeld half space problem, whereas today and in the last lesson we the problem. What is that? This is a sketch of the electromagnetic configuration. We have a uniform plane wave that impinges normally on a perfectly conducting half plane, that is a half plane which is an idealization of a very thin conductor. So we will neglect z direction, which is orthogonal to the half plane. And the uniform plane wave that impinges on this screen has the electric field parallel to the edge or rim of the half space. So by adopting the Cartesian reference frame as the one in this figure, the electric field is parallel to the y-axis. So the incident field can be written simply as a complex constant, E0 incident, times the unit vector of the y-axis, times the propagation exponential, which is characteristic of see that the direction of propagation is associated with the angle theta incident, which is the angle that the phase vector beta of the incident wave forms with the positive z-axis. Okay. Now the problem is to find the total field everywhere in space, and the total field is by definition the sum of the incident field plus the field due to the presence of the half plane. Here we have a first, but it's a half plane, of course. And the scatter field is due to the currents that will be established on this half plane. Okay, first of all, some history about this problem. The name Sommerfeld comes from the fact solution to this problem back in 1896. This is the first part of the relevant paper that was written in German. And this solution was obtained with a rather ad hoc approach, which is not amenable to be used in different problems. So it is not easily generalized, but however, it was historically the first exact solution to a diffraction problem. Okay. Subsequently, the same problem was addressed by a number of scientists. An important step was made in the 1940s when it was realized that a powerful complex analytical technique known as the Wiener-Hopf approach could be used in order to solve this problem, and this can be found in the historical papers by Edward Copson, for example, in 1946, and Carlson and Heinz in 19. A few years later, however, Paul Clemau in 1951 proposed an alternative approach, which is based on the so-called dual integral equations. That is somewhat simpler. It is very, very similar to the Wiener-Hopf approach. However, the formulation is simpler. Let me admit Edoardo. Ok. Buongiorno, Edoardo. And in particular, both approaches, the Wiener-Hopf and also its simpler formulation in terms of dual integral equations, are characterized by the fact that both employ in a crucial way complex analysis and were actually generalized to solve many different diffraction problems. For example, half planes or junctions made with materials on which impedance conditions, boundary conditions hold, or impedance transition conditions hold. So we can generalize both the geometry and the kind of boundary condition. And we will introduce in this and in the next lesson this Wiener-Hopf dual integral equation method. It is interesting that much later, in 1983, Professor Franco Gori, who was a professor here in Sapienza before moving to Roma Tre University, now he's retired, who was a teacher of optics in this university. He found that it was possible to express the solution to the Sommerfeld half-plane problem in elementary terms by introducing cylindrical functions of half-integer order. And this is actually the solution that we will address first because it's simpler and instructive. However, we will do that only after discussing some general concepts that will help us in entering this electromagnetic configuration. The electromagnetic configuration is repeated here. This is the perfectly conducting half plane. Again, this is a typo. That's not a half space, but it's a half plane. That's the incident plane wave that forms an angle theta I with respect to the normal z to the plane. Now note that this kind of configuration is translationally invariant with respect to the y direction. And furthermore, the incident field is also independent of the y coordinate. And furthermore, it is Tm polarized, since the magnetic field is orthogonal to the y plane, whereas the electric field has the only y component. So for these reasons, we may conclude, based only on these symmetry considerations, that the scattered field, and therefore also the total field, will be independent of the y coordinate and transverse magnetic as the incident field. Okay, so the only non-zero components of the entire fields are Ey, Hx, and Hz if we adopt a Cartesian reference frame. And in particular, if you know the electric field, you can know everything, because Maxwell equations allow you to derive the magnetic field in terms of the electric field in a standard way, okay, by taking derivatives. So our aim is to find the electric field everywhere. Now note that on the perfectly conducting plane, there will be some surface electric current density, which is related to the jump of the magnetic field. The usual electric density as the product of the unit vector z0 normal to the plane times the jump of the magnetic field. Since the magnetic field has only components along x and z, you will see that the only component that comes into play in this calculation is Hx. And in particular, the electric current will be directed along y. So we have a flow of current parallel to the edge of the half plane. And the amplitude of this flow is related to the jump of the x component of the magnetic field, which is equivalent, the jump of the z derivative of the y component of the electric field. Now, since the electric field, the total electric field, is the sum of the incident and scattered field, and since the incident field is continuous together with its derivatives everywhere in space, the field can have no jump. So instead of writing the total electric field here, you can also modify the expression by writing only the scattered part of the electric field, because that's the only part of the field that may have a jump somewhere. So the normal derivative of the scattered field is discontinuous across the perfectly conducting half plane, and of course this discontinuity is related to the existence of this surface electric current that flows on the plane parallel to the rim of the half plane. Is actually explicitly by introducing the domain half plane, which is the perfectly conducting half plane. So the half plane on z equals 0, where x is larger than or equal to 0. And the problem we will solve will be in the entire two-dimensional plane without this domain D. Let me admit somewhere here again, Andri. Okay. Disconnected for some reason. Okay, and okay, here in the two-dimensional xz plane, without the points on the perfectly conducting plane, what we need to solve is a classical two-dimensional Helmholtz equation for the electric field, or even for the scattered electric field only. And the scattered electric field must be equal and opposite to the incident field on the plane, so half plane. So on in the domain D, electric field, which is tangential to the perfectly conducting plane, half plane must be 0, perfectly conducting plane. Okay, so the scattered electric field must be equal to minus the electric field of the incident plane wave when z equals 0 and x is larger than or equal 0. Okay, this is the one in the box is the color problem. And in addition to these equations, what we still need to introduce is some information about the behavior of the field in the vicinity of what is the only geometrical singularity of this configuration, that is the edge. This is necessary injection. So if you wish to have a unique solution, you have to specify what is the behavior of the field in the vicinity of any geometrical singularity, which may be edges, as in this case, but also more generally vertices, for example, more general three-dimensional. Now, for instance, consider perfectly convenient internal angle alpha as in this figure, which is medium. You can assume that the electric field, the y component of the electric field in the polarization is very close to the edge. Draw can be represented, can be expanded asymptotically in terms of a power series, of which the dominant term is proportional to the nth power of rho. And Maxwell equations then we will allow to find elements that will be also expressed in terms of a power series proportional to rho to the power n minus 1. Okay. Now, generally, the behavior of the electromagnetic field close to some edge of angular regions like this one, or more generally also the electric, by enforcing the condition that the energy density of the electric and magnetic fields remains finite in any. This is the so-called edge condition that was introduced at the time by Meixner, and for this reason is also sometimes named the Meixner edge condition. If you do that on the specific, so in the previous slide, if you enforce the boundary conditions on the faces of the wedge, you can find actually the exponent n, which is called the singularity exponent, which is related to the internal angle of the wedge by this simple relation. N is given between pi and 2 pi minus alpha. So in the case of a perfectly conducting half plane in which the internal angle is 0, so alpha is equal to 0, this singularity exponent n becomes equal to 1/2, which means that the dominant asymptotic term of the electric field in the vicinity of the edge is equal to rho 1/2, so the square root of the distance of the edge. Whereas the components of the magnetic field density, Jz, on the half plane, will be dominated asymptotically by rho 2 minus 1/2. So they will be actually singular. the vicinity on a line and in a two-dimensional domain. Okay. Having said that, also consider some symmetry in the scattered field. This is produced by the current density on the perfectly potential. And since the plane z equals 0 is a symmetry plane for the scattered field, we can say the field is even symmetric with respect to the plane z equals 0, which means that if you calculate it at that, then if you calculate it at minus z, if you know the field, for example, in the half space where z is 0, okay, so you calculate the transmit the plane wave comes out. The problem of diffraction by a screen, and this is very general, not restricted to this particular configuration. The present one can be decomposed in. Okay, here we have Clementina. Good morning, Clementina. The two steps of any diffraction problem by a screen are so-called interaction problem that consists in finding the scattered field on the plane where the screen is, in this case, the plane z equals 0. Okay, so since in this case the field, the scattered field is not plane, since it's equal, that is our boundary condition. The scattered field remaining half plane, so where x is less than 0. Okay. Second, we have the propagation problem. That is to the plane in the half space now, where z is positive, strictly positive, having determined the field on the plane z equals 0, which is also known as an aperture field, which is an antenna jargon, of course. And we may note that the truly difficulty lies in the interaction problem, since once you know the field on the outer plane that equals 0, the propagation problem can in principle be solved by expressing at any point in the half space where z is positive by some which involve the aperture field. But this may be numerically cumbersome, but numerically. Problem will be that of solving the interaction problem. Once we know that, once we have solved that, however, we also find immediately some solution to some generalized. For example, if instead of having a TM incident wave, we had a TE incident wave, that is a wave that is parallel to the edge of the plane and whose electric field is instead orthogonal to the edge, as in the right part of this figure. Then we make use of the electromagnetic, the vector form of the so-called Fubine principle, which, as you may recall, consists in replacing the apertures with the screen. And by introduce metal where you have the aperture, you can relate the configuration, the original one, in which you have a TM incident wave on our back half plane with the dual configuration in which you have a TE incident plane wave and you have your half plane again. However, now this lies where x is negative instead of positive. And this is the magnetic field of this TE incident wave. Okay, the vector form of the principle actually tells us that, for example, the electric field can be particular the incident total magnetic field in the X. So if you solve the TM problem, you have immediately solution to the T problem, and vice versa. But it is also possible to generalize incident angle psi incident with respect to the y-axis. So now we have a y-dependence of the incident field expressed by, again, an exponential, of course, since we have a plane wave, in which you can see here you have k0 times the cosine of this angle psi incident, and therefore you recover the normal incidence case by letting this angle psi incident equal to pi over 2. So in that case, you would have no dependence on y. The remaining part of the exponential, the sine function, okay. And all in all, the incident wave, the incident electric field that expresses the dependence on y, and the remaining part that contains instead the dependence on x and z, and which is parameterized by 0, and also by the angles psi and theta of the incident wave. It is important to observe again symmetry in this configuration. This electric field is an eigenfunction of the operator along the y-axis. So if you translate the structure along the y-axis, that is, you add to y any quantity, you will find that the incident wave is a factor. That is because the dependence on y is given by an factor be increased by some quantity. Along the same axis, the scattered field the incident field. So we can write the scattered field as the same exponential along y, that is times some function of x and z parameterized by the incident and theta incident. Of course, the scattered field will not be a simple exponential function as the incident wave, but something much more complicated. That is what we wish to find. However, the point here is that if you have solved the problem for normal incidence, you can immediately obtain the solution for oblique incidence. That is, because if you compare the differential statement of the problem for normal incidence, you can see the two-dimensional Helmholtz equation for the scattered field in the xz plane, where you can see there is the wave number k0 squared, the boundary condition that involves the scattered field on the half plane. Just a moment, I have something probably from the chat. Valentina is writing that she's having connection issues. Do you experience the same?
Yeah, I apologize. Like it's just sometimes you freeze or your voice, like we lose half of a sentence. I don't know if it's my connection or it's other, or it's the faculty connection.
So maybe it was my fault because my microphone is not working properly. Can you hear me better now?
No, at least I was constantly able to hear you, but at some points I would lose half of a sentence. You would freeze, and it's like we are experiencing connection issues. So like not everything is.
Okay. So the problem must be the connection, since yes. No,
Yeah,
in that
I think
case,
so, but I'm
I'm
not sure.
afraid that I cannot be much helpful. So let's try to go on, and let's note that the internet. Thanks for writing.
Okay.
However, okay. What I was saying is that if you compare the problem for normal incidence with that for oblique incidence on the right, in which you have again the two-dimensional Helmholtz equation for the scattered part of the field. Now, however, in the Helmholtz equation, you don't have the wave number k0 squared, but you have only the transverse component of the wave numbers, so kt squared, where kt is k0 times the sine of the angle psi I. And the boundary conditions way, which is exactly the same as the previous one for normal incidence, but we replace k0 with kt, but everything else is the same. So since they are formally the same equations, need to have the same solution. So what we can see, the scattered field in the general oblique case, the left here, using the normal incident case, so 2 instead of psi on the right. However, you need to scale frequency. But apart from that, everything else is the same. So for any oblique incidence case, you can reduce to the normal incidence case up to a scaling of the frequency. That's the only operation to be done. And the scaling is, of course, that the frequency omega prime is equal to omega times the sine of the incident angle psi. Okay. So our very particular case, normal incidence, TM polarization, we can go more or less in every direction. So we can change polarization and change direction of incidence. So as I was mentioning at the beginning of this lesson, half-plane problem is actually that of introducing the Wiener-Hopf technique. However, before doing that, we will address the elementary found almost a century after Sommerfeld by Professor Franco Gori, which is anyway very instructive because it is based only on elementary waves, and in particular, he found in this nice, very short paper in optics communications that the solution could be found cylindrical waves of order 1/2. Note that the interaction problem, which is what we need to solve, can be solved in general in terms of a superposition of elementary solutions of the Helmholtz equation put by half plane where the perfect conductor lies. Okay, because everywhere else we cannot current. If you consider this particular element, which is the product of the exponential e to j k0 rho divided by the square root multiplied by the sine of psi over 2. So we have the cylindrical or polar angle psi divided by 2. We have that this is certainly a solution of the Helmholtz equation, at least for rho larger than 0, of course. But this is a solution in factored form because we have a trigonometric dependence on the coordinate psi with a coefficient 1/2, and here the remaining parts, the dependence on rho, is actually proportional to a Hankel function of order 1/2, because it turns out that 1/2 has this very simple form, analytic. Okay, that's not a transcendental. Now, this function is anisotropic because we have a dependence on phi, so the propagation is not the same in all directions. And furthermore, this solution has some discontinuities. In fact, if we calculate the magnetic field again from Maxwell equations, in cylindrical coordinates, the magnetic field will have the rho component and the phi component, and the rho component turns out to be proportional to the cosine of psi over that is proportional to the sine of psi over 2 as the sine of phi over 2 is continuous everywhere. It's continuous also when phi is equal to 0 or 2 pi. That is because there the sine function, whereas the cosine function, where phi is equal to 0, 1, where when psi is equal to 2 pi. That is because 2 pi divided by 2 is pi, and the cosine of pi is equal to -1. So we have a discontinuity exactly where the half plane is located. And this is a crucial observation, because now the magnetic current density that flows along y is proportional to the discontinuity of the magnetic field, and is therefore in general different from 0 when phi is equal to 0. So we have an elementary solution of the Helmholtz equation that is produced. This is the reason why this can be used as the brick to build the general. And in fact, what Gori did was to simply enforce a superposition, in particular by noting that this solution vanishes. Now, the electric field at any point on the x-axis will depend only on the waves originating on the right of that point. So you can imagine a continuous distribution of sources whose density is here called P of psi. Psi is the integration variable. And the electric field observed at some location x by the sources that are on the right of this location. So you need to integrate it. Okay. The integrand is, of course, the amplitude of the source, P of psi, that we introduced. So an exponential divided by a square root. Of course, the argument is now psi minus x, since we are referring this solution as positing psi along the half. P, which must be such that the scattered field be equal and opposite to the incident field on the entire half plane where x is larger than or equal to 0. And this will allow us to obtain an integral equation in the unknown. And in fact, if we enforce the boundary condition, we obtain an integral equation in which the unknown is p on the left-hand side inside the integral sign, and on the right side we have the field of the incident wave. Okay, this can be solved even if it may be immediate at a glance, but just change variables in the integrals. So you now let psi be equal to psi prime, so that now the integral is performed from 0 to plus infinity. Okay. Now, a moment thought will allow you to conclude that the unknown, that is p of psi, must be proportional to this exponent theta I psi. That is because if you this in psi prime plus x by the property of the exponential that factors when you calculate it on a sum, you will be able to factor the exponential in two terms, one of which will remain inside the integral because it depends on psi prime. And what you will get will be an integral in psi prime in which x has disappeared, whereas the entire dependence on x can be taken outside of the integral, be therefore written as a factor outside the integral, which replicates the exponential on the right-hand side. So we are basically able to balance the left and right-hand sides. The only point is to find the correct constant c here, so that everything is correct. And you do that by introducing this equation, and you will find that the constant c must be entity is satisfied. We have now removed the dependence on x, which is common to the left and right-hand sides, and also the dependence on the amplitude of the incident wave. So what remains is an integral on the left-hand side in psi prime, which can be, however, evaluated analytically by another simple change of variables. We introduce the new integration variable mu, whose square k0 psi prime times 1 plus the sine of theta I. If you do that, you take out of the integral the terms coming from the Jacobian. And the remaining integral is a complete integral. So that was one of the examples we evaluated at the beginning of this course. Its value can be expressed in elementary terms, and in particular, it's equal to e2 minus j pi over 4 times the square root of pi divided by 2. So from here, you can isolate the constant c, which has this expression here at the bottom in terms of known quantities. And finally, we have the solution, therefore. The solution is the following. The scattered field on the entire aperture plane, 0, will be equal to minus the incident field, where we have the perfect conductor. So we have an exponential dependence when x is larger than or equal to 0. Whereas on the remaining part of the aperture plane, in terms of a complex frenetic integral, by means of the solution that we have just derived. Once we, as I mentioned before, we may know everything. So the aperture field can also be called Sommerfeld integrals, which is the usual denomination in optics, where scalar approximation is often introduced. In this case, this is not an approximation because the problem is scalar by itself. Alternatively, you may exploit this particular form of the solution that we have built, since we have built the solution as a superposition of force the boundary condition. We can use the same representation to find the field everywhere in space. So you can again use the A, which is a superposition with amplitude P, and now P has been found, of elementary waves of anisotropic character. Of course, all those waves originate from the general policy in terms of polar coordinates referred to this general point psi. So you can see here rho prime and phi prime, which are related to this origin psi and connect the origin psi to the observation point. Okay, so that's another possibility to evaluate the field everywhere. Okay, this is more or less everything. So as you can see, this is quite elementary. We have introduced an elementary solution of the Helmholtz equation and a block able to enforce the boundary condition. Of course, in the second part of this lesson, after the break that we will now do, we will see a more general approach to the same problem, which is based on the Wiener-Hopf method, and which will give us the chance of employing in a very clever way concepts from complex analysis here. And so let's make a break of 10 minutes. Let's restart at 10:55 or so. Okay, hoping that the internet will go better in the second part. So see you later. So back again to our, so we will now address the dual integral equation formulator. Now, this is a classical way of approaching this kind of problem, particularly because it can be generalized to related configurations. For example, the half plane with an impedance boundary condition, or a transition two-part impedance plane. There is an entire plane divided into two half planes where different can be addressed with the Wiener-Hopf method. Now, in short, the analytical solution of the integral equation that results from enforcing the boundary condition is obtained using the Wiener-Hopf method, Bast's form of the integral equation, and therefore reducing it to some kind of functional equation, which is solved by invoking particular properties of the analytic functions, and in particular, the crucial property is the theorem for entire functions. We explained what is the Liouville theorem in our second lesson of this course. That was a consequence of Cauchy theorem, which can be easily generalized to a form that is explained clearly, for example, on Wikipedia. Now, since in this process, the crucial step, also the most difficult step of the method, consists in factorizing a given function into the product of functions that are analytic and without zeros in the upper and lower halves of the complex plane. The method is also known as the factorization method. This is the most common denomination in the Integrand, typically the Soviet literature. Okay. Now, there is a mathematical method that is somewhat more direct, since it works directly with the spectra of the field quantities. And that was proposed by Paul Clemau in 1950 based on dual integral equations. This is the method that we will adopt here to a solution. Again, we consider the case of temporalization. And today we will consider only the case of a perfect conductor. And the last lesson of this will generalize the approach to the case of. Note also that in the second part of this lesson, I have changed the reference system. So now the incidence plane is the XY plane, whereas the edge of the half plane is the direction of invariance of this configuration, which is not anymore the y-axis, but I am adopting what is the most in the treatment. And in particular, this is a beautiful book by Skinner and Boakis, Approximate Boundary Conditions in Electromagnetics, from which I have taken most of the material that will follow. Note now indicated with with the angle phi. Phi sub-observation angle is the usual polar angle phi. As before, is the distance of the half plane. The key feature of the dual uses a priori a particular representation of the field, which is known as the angular spectrum, so that we write the scattered field, the electric and magnetic fields in particular, the only component, the Z component of the electric field, and the X component of the scattered field, magnetic field. These angular spectra function, which is known for the moment, that depends on the cosine of this angle alpha, which is the integration variable. And then there is potential of planes which propagate alpha. So the situation is the one depicted in the bottom figure. This kind of representation expresses the fact that if you have a distribution of surface electric current density on the plane where our scatterer is located, and this current density is directed along Z, and this current density will produce a spectrum of plane waves, and in which here I have written explicitly a pair of them. I have written the plane wave that propagates at an angle alpha with respect to the x-axis, and the symmetric one, which propagates at the angle minus alpha, okay, whose electric field lies in the x-y plane. So, since we are here considering the x component of the magnetic field, you see that in addition to this impedance that scales the amplitude of the electromagnetic field, of alpha, which takes into account the oblique propagation of the that when you have grazing propagation, the magnetic field will be vertical, and therefore the x component will be 0. And this is taken into account by this sine function. Whereas when you have propagation along y, alpha is equal to pi over 2, and the magnetic field is entirely directed along x. Note that this representation holds both in the upper and lower half spaces, where there is field is even symmetric, so there is no sign difference, whereas the magnetic field is odd symmetric, in particular the x component, have a plus minus sign. Also, we have plus minus sign in the exponential, take into account the different propagation directions, the two half planes, y n or less than 0. Okay, this is starting point. Okay, and however, what is the integration range in this integral? So what kind of angles should we take on? Okay, we can answer this question by considering explicitly the spectral representation of the field. So we may write the scattered field as a superposition that are produced by current flowing on the plane y0, each elementary current giving rise to a contribution that is weighted by the two-dimensional Green's function for the scalar Helmholtz equation, and is proportional to the time we have, and for scalar equation and time. Okay. In particular, if we observe that y equals 0, what we get is that the Hankel function has x minus x prime, and that we need to perform becomes a convolution, that is a configuration along the x-axis. So we have, apart from this constant minus j omega mu 0, we have the convolution between the surface current density and the two-dimensional Green's function. From the spectral domain, as it is to say, with the tilde above, proportional to the electric current j tilde, the Fourier transform which is for equal to 1 divided by 2jy. For the vertical wave number, so we have to use the separation condition. So we have the square root of k squared in the so-called visible range, where kx is less than k0, whereas we have minus j square root of kx squared minus k0 squared in the so-called invisible range, in the range where the plane waves of this spectrum, and so therefore they will be evanescent along y. So if you now, let's go, it is typical of Helmholtz. We find the electric field will be given having the numerator here, e2 minus j, and finally you can recover this, the electric field in the spatial domain by inverse Fourier transform. So you have this integral representation of the scattered electric field as an inverse Fourier transform under an integral made with respect to the kx spectral variable. To get our desired plane wave spectrum representation. In particular, we may introduce, which is a normalized form of kx, it is equal to kx divided by k0. Then variable alpha, okay, so that I can be 1 minus times the sine of alpha. The situation of the singularities in the complex planes of these new variables is represented in here, and more details will be clearer and given. Consider, for example, the lambda plane. In this plane, we have the usual branch points at minus and plus 1. Those are related to the branch point at plus or minus k0 in the complex plane of the kx variable. But since we are normalizing to k0, that at plus the associated those as the Sommerfeld branch cuts, as introduced last week. So they are hyperbolas that, in this case, since we are considering a vacuum, positive and negative imaginary axis, so the weakly lines in yellow. We also have a pole singularity, but we will address that later. So here we just notice that the integration range in kx was the entire real axis. So in the lambda plane, that must all the integration must be indented, of course, to avoid singularities, and this is the correct way to indent. If you now revert to the alpha variable, which is an angular variable, the real axis is mapped into this contour C, which is made of the vertical path on the negative imaginary axis. Then we have a horizontal path from 0 to pi, and a semi-vertical path again in at least parallel. It's our electric field in an integral with respect to alpha, and this integral, the spectral electric surface current density, J argument K0. So if you now include you may define this red particle incident, the amplitude of the incident field, times a function of the cosine alpha that we may call P sub E. Calculated at the beginning for the electric field. From Maxwell equations, you have the magnetic field in the form that we also introduced at the beginning. So from spectral considerations, presentation of the field, and also we have found what is the correct integration path. Now, once we have this, we can use alternatively the lambda variable And here is the expression of the plane wave spectrum representation of the fields in terms of the lambda variable. Since we have lambda in this case, the Jacobian will introduce this square root of 1 minus lambda squared in the denominator for the electric field, which is instead absent in the magnetic field because that square root is actually the sign of alpha that was already present in the expression of the magnetic field, so that is cancelled by the Jacobian. So you see a simpler expression for the magnetic field here. It is convenient to work with this lambda variable in order to enforce our conditions, as we will now see. In particular, we can write the electric field right on using the lambda variable again, and the expression is this one. It is proportional to the amplitude of the incident. Now contains the unknown function t sub e, which is the spectrum, the root of 1 minus lambda squared, and a simple exponential e2 minus j. So now we are ready to enforce the boundary condition on the perfectly conducting half plane. Which tells us that the sum of the scattered and the incident field must be equal to 0 there. So we will let the integral that we find in the scattered field, the exponential that characterizes the incident k0x cosine of must hold at any point on the for any x larger than 0. That could also be equal to 0 actually. Okay, so integral equation in which the unknown is the spectrum E sub E, okay, and the right hand side for any x that would be a Fourier transform. The Fourier transform. However, we would just have a scattered field. In this case, the situation is complicated. Another integral equation, and we can find it from the boundary condition for the magnetic field. Now, magnetic field, as we odds to y by symmetry, and in particular, if you 0, since it is odd, you will find that the scattered field on the we know that the jump of the exponent of this related current density, which flows surface current density, however, flows only where the perfect conductor exists, so only when x is positive, equal to 0. So therefore, the magnetic when x is less than 0. But since it is odd, then this means that the magnetic field must be 0, right? Exactly 0 when x is less than 0 on the upper plane. The integral this integral equation holds when x is less than 0. That is, the inverse Fourier must be 0 this from a that the spectrum is proportional to the spectral electric surface density. Now, since the electric surface density can in terms of integral that involves the spectrum p sub e of lambda. Now, see again. again, we find the integral equation in the lower box, which is the same as in the previous. So all in all, what we have found is a pair of integral equations. One comes from the boundary condition for electric field, and that holds geometry considerations, or from the magnetic field, and the surface integral equation holds when x is negative. Okay, whenever you have a situation of this kind in which you have a common unknown to a pair of integral equations, which, however, you can see in the upper integral equation, you have the square significant in the lower integral equation. Hold in complementary domains, as in this case, in two complementary half planes, in terms of dual integral equations. And there is a whole literature on the possible. See in this lesson is an inner Hopf approach and makes direct use of complex analysis. Okay, so this is our all the steps is to solve these dual integral equations. And the first step is to note that the spectrum is not an arbitrary function, actually an analytic function of lambda, at least in the upper half plane of the complex lambda plane. To see that, we may change the spectrum and transform of the surface current density, so which is written explicitly here. So the spectrum is up to some constants, basically the Fourier transform of the surface current density. This is the integral written here. Since that exists for positive, now this fact geometry contour in the upper half of lambda. Find is on the right. One is performed that is a contour in the lambda complex plane. However, if you now assume that you are working in the other lambda, these will also and we are in the condition to make use of the Fubine theorem, which is the theorem that allows you to switch the order of integrations in an integration made with respect to more than one variable. So basically, we switch the order of integrations and we perform a integral along x, as is written here. Lambda is now just a simple exponential function, and the exponential function is an entire function. It is analytic everywhere. So by Cauchy theorem, its integral along any closed contour would be equal to 0. And so therefore, this entire quantity will be equal to 0. So we have discovered that if you integrate the spectrum along any closed curve gamma, the result is equal to 0. Now we make use of Morera's theorem, which is, if you thought of converse of Cauchy theorem, that integrating is an analytic function in the upper half plane. We will make this explicit by changing name to the spectrum. So from now on, the spectrum will be indicated with the name U, capital U. Just to recall us that we are considering a function that is analytic in the upper, u is the initial of upper half plane of the lambda variable, okay? So just by this observation, we have been able to satisfy the solution of our pair of dual integral equations. That is because if the function u is analytic in the upper half plane, this will be the one that comes from the Dirichlet field. And that integral equation involves a more complicated kernel, because now we use lambda squared. And for products. And the lower half place here, the integral equation behaves well, it goes to 0 at infinity. So we may now run on the entire real axis with this semicircular contour that has an infinite radius. The contribution of this semicircular contour will be equal to 0 because the exponential goes to 0 at infinity in the lower half plane. Why is it useful to close the contour? Well, because more residues. And since you wish to obtain this kind of right side, we are now able to postulate a form for function which is the ratio of u of lambda and the square root of 1 minus lambda squared. This function must have the right singularities so that by means we're exactly the right hand side. If you think a moment, you just need to see minus lambda 0, where lambda 0 is equal to the cosine of phi. And this is introduced by this ratio with lambda plus lambda 0. Then also an arbitrary numerator as long as the function is an important constant here, so that the residue theorem together with this divided by 2 pi j will give you correct to -1. And finally, you can add another arbitrary function of half plane, since it will function to the residue theorem, since by Cauchy theorem on a closer contour. So basic here is to enforce the presence of a pole such that you recover exactly the right hand side of the equation. Now the point is to what is bounding in the upper half plane, and we do not know neither L1 nor L2, which are functions analytic in the zone. They are indicated with the letter L, is initial of lower. So they are lower functions. Information that we get with functions, that is the analyticity in the upper or lower half planes, are quite surprisingly to be in combination possible. And this is what we will illustrate next. Those functions is to try to rewrite what you can split the dependence on electricity and lower function. which gives the factorization method. Some complex function as so function f of lambda of f plus and f minus, where f plus is called the so-called split functions. Those are functions that are analytic respectively in the upper they also are without zeros respectively in the upper and lower half plane. If you have the function by the second order inside the square root and then factoring the square root minus lambda, the square root of 1 plus lambda. Now, the square root of 1 minus lambda turns out to be an upper split function since it's singular at +1, and this means that lower actually, this will be the lower functions, whereas the other one will be analytic in the upper. This is actually what we need in our specific problem, because that's the only function that still remains to be factored. In particular, if you consider this equality, u and l are functions that are already either upper or lower, whereas the square root of 1 minus lambda squared is neither upper nor lower, but since it can be factoried and leave on the left-hand side of this equality its upper part, and take on the right-hand side the lower part. Okay, so we have k plus and on the right of digitize both up. Still one step to do, because there is the pole. Now the pole is 0. Plane. So we need to remove it from the right hand. Sorry, it's upper, actually not lower. And we should remove it from the right hand side. We do that by subtracting from the right quantity, in particular the quantity to be the optical pole. So you can see there is in this term here there is. However, in the numerator, we have a constant, which is k plus, evaluated at lambda 0. Why exactly this constant? Because constant such that what is happening on the right-hand side, and in particular, the brackets not inside the bracket. Zero when you evaluate it at the optical pole. That is because k minus is equal to that minus lambda. And therefore, this quantity will be equal to 0 at minus lambda 0. So what we have done is that we have removed by so that OC on the left-hand side is entirely analytic in the upper half plane, whereas okay, the right-hand side. So we have split the upper things on the left and the lower infinity of those functions, and that can be inferred from the edge condition for the surface current density. That is because if we know the local asymptotic behavior of the surface current density close to the edge, and we know by over 2 I mentioned first part of this lesson, we may conclude that which is proportional to the explanation rule. We go to infinity as lambda to minus. So we know the order of asymptotic decay of the spectrum at infinity. It is occurring in the equation we have obtained so far is by case, for example, this looks one half, where we have just nature plus is the square root of the like lambda to 1/2, and therefore we'll go to lambda to -1. It's then like see lambda over -1/2. Okay, so all in all, we have an asymptotic decay to infinity. So since this is asymptotically decaying to infinity, what we have of the we have got this one are respectively an upper function on the left and the lower function on the right. But since they are equal, this means that both are analytic everywhere. Actually, in infinitesimal at infinity, that they are bounded. Not says that if you have none, that function must be constant. Must be equal to 0. It's not equal. That is 1 here. So the spectrum, that is the upper function u, because it is known. If you do that, you will discover that the spectrum plus lambda 0. So the ratio between divided by 0. Or if you prefer, the variable lambda 12, which was our initial angular variable in the plane wave spectrum. PE of cosine of alpha is this function in the box. I have just discovered that my microphone was not working. C'è risposta. Can you hear me now? Ah, okay. So long was this problem with the microphone? I mean, would you follow the last part of the lesson? I cannot hear you for some reason. So today there must be some serious. Okay. Case I will leave you, of course, and I will check on the recording how long was this disconnection of the audio. Okay, I'll greet you, and I'm not sure you can hear me now, but anyway, see you on Thursday.
Grazie mille professore, buona giornata.
Ciao da oggi.
See you. Thank you.
Se dovrei prima interrompere.